At this point in Chapter 9, we've covered the first two sections, which are temperature and thermal equilibrium and defining heat. Finally, we're moving on to Chapter 9.3, which is changes in temperature and phase. Before we can even look at changes in an object's temperature, we have to know about specific heat capacity. This is defined as the quantity of heat required to raise 1 kilogram of homogeneous material by 1 degree Celsius, given constant pressure and volume. So, in other words, different substances will have different temperature changes under the same conditions. Objects that are faster at absorbing heat will have a larger temperature change, or a smaller specific heat capacity, while objects that absorb heat less rapidly will have a smaller temperature change with the same conditions. We define specific heat capacity as Q, or the energy transferred as heat, divided by the mass of the object, m, times delta T, which is the change in temperature. Therefore, the units for specific heat capacity are joules divided by kilograms degrees Celsius, and this equation will be very helpful in calculations coming up in this section. One method that will come up in many problems that concern specific heat capacity is calorimetry. This is defined as the procedure used to measure the heat transfer from one substance to another. So a calorimeter is this device that I have tried to draw below. It's basically a system in which water is stored in a chamber, its temperature is recorded, and then a test substance is placed in the water. Since we know the specific heat capacity of water, and we know that the energy transfer between the two objects must be equal, we can solve using this calorimeter for the specific heat capacity of the test substance. We'll be looking at some applications of this later on. As substances undergo changes in temperature, they eventually reach the point of phase change. A phase change is when a substance changes from one state, so either solid, liquid, or gas, to another at constant temperature and pressure. The graph I've sort of tried to replicate below shows the temperature of an object as a result of the energy or added heat. This graph is not a straight line, as one might suspect. Instead, it's a line that plateaus at certain points, right here and up here. I've also labeled the 3 states of matter. At the bottom we have ice. This is a graph for water, by the way. In the middle we have water, and finally we have steam. So the places where the graph levels out are places where phase changes are taking place. You can see from the graph that during phase change, temperature does not increase. Temperature remains constant. In other words, the temperature and the phase cannot change at the same time. You may have also noticed that because this is a graph with the Celsius scale, the changes in phase occur at the melting and boiling points that we've defined for Celsius. So it turns from ice to water at 0 degrees, and then from water to steam at 100 degrees. During phase change, the energy that is added or removed per unit mass is known as latent heat, which we write with the variable L. Because phase and temperature can't change at the same time, latent heat accounts for the extra energy that's added or removed during phase change. And below I've written this equation for energy transferred, or Q. This is equal to mass times latent heat. Later on, this equation will begin to show us how much energy is required for a phase change to take place. Let's look more closely at these 2 points where phase changes occur. Latent heat will come into play in both of these locations. In the first, it's known as the heat of fusion, which is the energy needed to transfer between the solid and liquid phases. Later on, when the water transitions to steam, we use the heat of vaporization. This is also latent heat, but it's defined as the energy needed to transfer between the liquid and gas phases. Now for some practice problems. Number 1. What is the final temperature when a 3 kilogram gold bar at 99 degrees Celsius is dropped into 0.22 kilograms of water at 25 degrees Celsius? So the first concept to keep in mind for this problem is that the energy that is gained by the water via heat when the gold is dropped into it will equal the energy lost by the gold, which we'll call negative Q sub G, because it's energy being lost. We also know the equation that specific heat capacity, or C sub P, is equal to Q divided by m delta T, or Q divided by M times the final temperature minus the initial temperature. That's the change in temperature. If we multiply this denominator to the other side, we have an equation for Q because we've isolated it by itself. So we have Q will be equal to the specific heat capacity times the mass of the object times the difference between its final temperature and its initial temperature. Now that we have this value for Q, we can plug it into the equation I've written at the top. So we'll start with the water. Q sub W, or the energy gained by the water, will be equal to the specific heat capacity of the water times the mass of the water times the final temperature minus the initial temperature of the water. On the other side, we have a negative Q, and then Q for the gold will be equal to the specific heat capacity of the gold times the mass of the gold times final temperature minus initial temperature of the gold. Now we can plug in all of the variables we know. And we have, by the way, we have these known facts over on the side, which are the specific heat capacities for both gold and water. For water, we have 4,186. The mass of the water is 0.22 kilograms. The final temperature is unknown, that's what we're solving for. The initial temperature is 25 degrees. On the other side, we have a negative sign, then we have 129 for the gold, times 3 kilograms, times this final temperature minus its initial temperature of 99 degrees. Now I'm going to distribute some of these values, so I end up with 920.92 times the final temperature minus 23023. I got this just by multiplying these two values and then distributing them into these parentheses, by the way. Then on the other side, I'll distribute again to get that negative 387 times the final temperature plus 38,313. That's also just through distribution. If I simplify by adding to eliminate this value, and also adding the 23,023 to the other side, I get that 1,307.92 times the final temperature equals 61,336. I'm running out of room here a little bit, but I'll divide both sides by 1,307.92 to get T final by itself. So the final temperature of the entire system will be equal to about 46.9 degrees Celsius. Number 2. How much heat is required to change the temperature of a 0.4 kilogram stainless steel spoon from 20 degrees Celsius to 50 degrees Celsius if the specific heat capacity of stainless steel is 500 joules per kilogram degrees Celsius? So we're going to be using the same equation that we used in the first problem, where the specific heat capacity of an object is equal to the energy required for this heat transfer divided by mass times the change in temperature. Now we have all the variables that we'll need to solve. So we know the specific heat capacity, that's 500. We're solving for Q, that's how much heat is required. The mass is 0.04 kilograms, and delta T, or the change in temperature, will be the final temperature, 50 degrees Celsius, minus the initial temperature of 20 degrees Celsius. Now I'm simply going to multiply this denominator over to the other side to isolate Q. And I get that Q equals 600 joules. That's how much energy is required to heat the spoon. Number 3. A 0.0255 kilogram silver ring, which has a specific heat capacity of 234 joules per kilogram degrees Celsius, is heated to 84 degrees Celsius and then placed in a calorimeter containing 0.05 kilograms of water at 24 degrees Celsius. The calorimeter is not perfectly insulated, so 0.14 kilojoules of energy are transferred to the surroundings before a final temperature is reached. What is the final temperature of the entire system? Okay, so the very first thing to do would be to convert these units to joules, just to make sure that we don't make this mistake later on. So a kilojoule is 1,000 joules, so 0.14 kilojoules would be 140 joules. So in most situations involving calorimeters, we would know that the total energy is conserved, and that's how we would calculate the answers. However, in this case, they've told us specifically that total energy is not conserved because some energy is lost. So we'll still set up our equation with the energy gained by the water, which will be equal to the energy lost by the ring. However, since there's this additional energy lost to the surrounding environment, we also need to subtract those 140 joules. Now we're ready to plug in our substitutions. So we have, and this is a repeat from problem 1. If you need to refer back to that to see how I'm getting to these variables, then go back to problem 1. So we have specific heat capacity of water times the mass of the water times final temperature minus the initial temperature of the water. That's all equal to negative specific heat capacity of the ring, I'll call that R, times mass of the ring, times final temperature minus initial temperature of the ring, and then also minus 140 because that's this lost energy that we have. Now we're ready to plug in the values. So we know that the specific heat capacity of water is 4,186. I've looked that up from before. The mass of the water in this equation is 0.05 kilograms. Final temperature is unknown. And then the initial temperature of the water is 24 degrees. We know that the specific heat capacity for the silver ring is 234. Then its mass is 0.0255. We still have this final temperature that's unknown, minus its initial temperature of 84 degrees, and then that all minus 140. Now I'm going to multiply some of these values together and distribute. I'll do this on both sides to simplify this equation. I'm left with 209.3 times the final temperature minus 5,023.2 equals negative 5.967 times the final temperature plus 501.288 minus 140. Finally, I can simplify by adding this temperature final over to the other side. That cancels this out. And then I'll add this 5,023.2 also to both sides. Simplifying all of that with the calculator and dividing, I get that the final temperature of the system is about 25 degrees Celsius. This has been Chapter 9 of Physics. We've covered multiple topics surrounding heat, including thermal equilibrium, changes in temperature and phase, and some ways to define heat. Thank you for watching.